Hello, everyone. I am appreciated to join the international conference on frontier computing. This is my paper title, an enhanced adapted neighborhood adjustment strategy on MOEAD for EEG singles decomposition-based big data optimization. I am the speaker of this time. My name is Meng. Other authors include Yuanfang Chen, Wang, and Jiaming Chen. Uh, Our paper will describe according 5 sections: background, related work, method, impairment and loss, and conclusions. The first part is background. As the world becomes more connected, more and more data is being collected, leading to the generation of whole volumes of structured and unstructured data, commonly referred to as big data. The big data has 3 characteristics: volumes, variety, and viscosity. This corresponds to 3 aspects: data quantity, data type, and requirement to process data. And this corresponds to 3 challenges of optimization method: massive number of decision variables, different mathematical properties of the objective function, and the computational time requirement required. The problem areas that can benefit from optimization big data: healthcare, the public sector, cybersecurity, uh, local stakes, air traffic, retail, manufacturing, and defense sectors. EEG singles through independent competent analysis with to some intent approximate a big optimization problem, as it requires a real-time handling of EEG singles. The traditional optimization technology has these drawbacks: only one function, lack of parallelism, and long time to get satisfactory solutions. So researchers towards the modern intelligent optimization technology, swarm intelligence, evolutionary algorithm. Evolution algorithms are population-based heuristic search measures that have demonstrated great success in solving complex optimization problems. This has shown in powerful search capability, but EA for big data optimization still visiting some problems. Numerous decision variables affect the convergence rate or not get satisfactory solutions of EA. The part 2 related work. Here, we need to distinguish between single objective and multi-objective problems. Suppose I need to equip a computer. I need to consider 3 variables: CPU, GPU, and ROM. If it is a single objective problem, we only have one price, the one objectives. Where for multi-objective problem, we have to consider 3 objectives such as price, performance, and environmental protection. We need to find a compromise among these 3 objectives. This is the MOEAD framework. Step 1 is installation. We need to initialize population. The calculate the neighborhood in its weight, and we call it the BI, and reference point. The reference point is good direction for all population. Step 2, if the iteration is not stopped, we need to update the solution. In MOEAD, we firstly to random select 2 parents from BI to produce new solutions. In these substeps, it include selection, mutation, and crossover. Then we need to update the reference point. Last, we need to update its neighborhood solution. According to Chebyshev distance, this achieves a fast convergence of the solution. This is a very smart operation. The part 3 is method. MOED ANA is a algorithm is published in Journal of Bell-Inspired Computing. This idea of MOED ENA from MOED ANA, which combines neighborhood adjustment strategy and different crossover operators. Why we design this neighborhood adjustment operator? Because in MOED experiment, we find the neighborhood size is fixed value in MOED, but for some populations, such as lambda 3, just have related solutions in its around, such as lambda 4, it has many solutions in its around. So we need dynamic adjustment to the neighborhood size. This is a novel idea. It keeps the MOED NA has better diversity than MOEAD. The details you can reference our paper. Next problem is how to compute the density of solutions. These two formulas imply how to calculate the distance of each population. For some of the big data optimization, we propose the MOEAD ENA with two variables decision may difficult to solve. So we designed the composite operator selection strategy. The three operators include D range 1, the most traditional operators in MOED, D range 2, increasing population diversity by more parent population joining the crossover operator. The center of mass crossover, the symmetry Berry crossover operator. How to select every crossover operator? The fitness rate rank based multi-armed bandit operator selection strategy, FRRMAB, is proposed. In the FRRMAB, the fitness improvement rate saved in a sliding window, similar to the quail. It's designed a matrix, where the first row is used to store operator numbers used in the proposed generation, such as OP1, OP2, and OP3. And the second row is used to record the fitness improvement rate, FIR of the offspring, generated by its operator, and the FIR can be used with a following mathematics 2 to 5. We can select the flag of a crossover operator in next iteration. This is a framework of MOED ENA. The part 4 is impairment and results. In this state, we have 6 state sites: state 4 with 9, state 12 with 9, state 19 with 9. It's assumed that the X is a large matrix. Its dimension is n multiplied m. N% the number of time series, and m is the length of each time series. In this computation, each time series m is of length 256, and the number of time series n are 4, 3, and 19. This is a channel. S has the same dimension with n. A is a small dimension, n multiply n as a transformation matrix. C is a Pearson correction matrix. D is standard deviation. Beta is a standard deviation. We abstract this problem into an optimization problem. The first objective is the orthogonal element of C to 0 where mean time. Maximizing the diagonal element. The second objective function is to minimize the distance between the two matrices S1 and S. We compare MUAD ENA with MOEAD and NIDA2. This is impairment parameters. The bottom is the evaluate matrix. The score function calculated based on the 215 big data optimization computation. The score metric value is larger, the better performance of the S1 close to S. The score of can be expressed by the following formula 10. This is a score obtained by 3 algorithms for single and multi-objective problem. We will got outstanding performance. Figure shows the comparison results of 5 solutions chosen from the Pareto side of the purpose algorithm according to the baseline algorithm. From results previously described, it can be noticed that the new approach achieved better results than the other algorithms. The reason for these results are the good ability of the proposed algorithm to maintain a balance between exploration of search space and feature exploration, which improves the convergence curve and reduces the routing time required. The part 5 is the conclusion. In this paper, the MOEA of the framework was proposed, which enabled the optive neighborhood size adjustment and compose operator selection. In the experiment, 6 benchmark problems from the optimization of big data 2015 computation are used to validate the performance of MOEA ENA for big opt. The experimental results shows that the MOEA ENA clearly outperforms the baseline algorithm. In future research, it could be applied to various applications, such as a multi-objective algorithm for EEG classification for big data optimization problem. Thank you for listening.